previous lecture, we have computed the performance of a magnet without fading. Although we were able to get a expression, it was not very simple. It was complex, and it was not in closed form. It may be difficult to derive any insights from the expressions. So now we then made an approximation and only considered Dominic interference. So that will give you an upper bound, but it will not again be exact. Uh, so now we study a more realistic system, which is managed with fading. And we will see that how inclusion of fading, which is actually a realistic assumption, will make the expression simpler. So I'll talk about fading first, but I'm not going to discuss it in detail. You can review it from any wireless course. So when in the past, when we are talking about these wireless links, we saw that the whatever is being transmitted from the transmitter, it reaches the receiver, but a significant amount of power is lost in between due to the wavefront expanding in the space. Along with that, there are other factors also, other path losses also, which can change the received power. So few of them are, for example, if you have a blockage in between. So if there are buildings, trees, or even people, sometimes they block the signal, and that can reduce the power significantly. These are known as large-scale fading and shadowing. Large scale because they do not change that much fast in time. If there is a tree, you may expect it to be there always. If there is a person, then still it can be there in 1 second. And 1 second is a large scale, large time for wireless propagation because here we are talking about symbols which are less than milliseconds. And then there can be scatterers, which can include dust particles, raindrops, clouds, uh, which can change the phase or add attenuation to the signals. These are small scale fading, right? So what happens? There are multiple scatterers and the signal passes through them. It creates multipaths with different attenuation and phases. And when it finally gets added at the receiver, you may see a destruction of the signal or a construction of the signal, right? So sometimes the fading can actually increase the signal power because you may have multiple paths adding up to a receiver, or it can decrease if you have a distance, if there's interference from this path. And you cannot actually predict it. It's very fast and it changes as you move even a small distance in the space. So these two things will cause variation in terms of attenuation or the of the signal magnitude or the phase shifts in the signal. So when I talk about large scale, this I already covered at 1 GHz frequencies. 1 millisecond is the large duration of time, even if something is there for 1 millisecond. So what the difference mainly is when you see large scale fading, right? You expect it to be there, right? You can predict that it's going to be there for some time. So you of course don't want to connect to the base station, which is having a very high loss due to large scale fading, because you're not going to expect get any signal from that. Okay, and that performance is going to be bad. But when we talk about the small scale feeding, that may change over time. So you can do various kind of coding over it. You don't transmit when the fading is bad, where you transmit more when you get a very good channel. So all these kind of things are there. Okay, and how do we model the small scale feeding? I'll talk about the large scale feeding later on. But first, let us see how do we model the small scale feeding. So small scale feeding is generally modeled using some random variables because it's caused by unexpected random vectors. So such as random traffic, dynamic users, presence of airborne scatterers. So because of that, is you cannot predict the small scale feeding. So we generally model using some random coefficients, right? So Effect of fading can be incorporated into receive power as an effective gain factor or attenuation. Both is correct. Because sometimes the fading can give you gain in the channel and sometimes it will give you the loss in the channel. And we model the effective impact of these random factors by a random variable, A, which denote the gain in the signal stream. It is intuitive to assume that A is a complex variable because the angle of it will tell how much phase has shifted, and the magnitude will tell how much is the gain in the signal amplitude. So norm mod of A will tell you the gain in the signal amplitude, and the argument shows the shift in the phase of the signal. And eventually, this is the gain in the signal. So the gain in the amplitude power of the gain in the power of the signal would be G square, okay, which is mod A square. And the distribution of this G or H depends on the channel environment, right, from which the name of various fading is derived. So as you see, change channel, are you or you change the environment around you, you may expect a different type of fading, right? It also depends on the frequency, carrier frequency you are talking about. So incorporating all those factors, you have to find out what is the distribution of this G, right, by doing some empirical studies, right? So people have come up with standards fading, which they expect in different environments. So first one is known as the Rayleigh fading, right? This expect fading you would expect when you are in a very rich scatter environment. There are enough scatterers to scatter to create multipaths. So in this case, what happens is the random variable which denote the gain in the signal amplitude G, which is actually equal to square root of the H, that follows the Rayleigh distribution with parameter sigma, right? So what is the Rayleigh distribution? It has this, any random variable which has this kind of PDF uh, is known as the Rayleigh distributed random variable. So G follows this particular parameter, right, and with parameter C. And if I calculate the gain in the signal power, so the signal power amplitude, the gain in the power, if you calculate it, that is equal to G square, and its distribution is given exponential. So if G has the distribution of exponential Rayleigh distribution, then G square which is H, would have a distribution of exponential, right? And its distribution in particular will be given by this. Again, this is a parameter, its parameter is 2 sigma square. So its mean would be 2 sigma square. So normally we take it as a unit mean, and all the constant, like all the average gain, which is the mean, we can incorporate in the part loss itself. The second is the Rician fading. So second one is the Rician fading. And you expect Rician fading when there is a line of sight path and multiple non-line of sight paths. And it is used when there is a direct line of sight path together with one or more non-line of sight paths. Okay. So in that case, the power from the line of sight is generally higher than the non-line of sight path. And the distribution looks like something similar to this. And if the ratio is k, let the ratio between these two is k, then the received signal amplitude is rise distributed with parameter nu square equal to k upon 1 plus k omega and sigma square omega upon 2 1 plus k. So there are two parameters here, k and omega, and there or you can write in terms of nu square and sigma square, and the shape parameter is known as nu, and the resultant PDF would be in this format. So this is the Bessel function. So it's the expression is actually a little bit complicated to work with. And then we have Nagami fading. It's a generalized version of Rayleigh fading. It says that uh, when we have Nagami fading, then it means the signal amplitude follows the Nagami distribution with parameter sigma, and its distribution is given in the following format. In that case, H, which is G square, follows the gamma distribution, uh, right, which has the following distribution. So in that case, the distribution look like something similar to that. Right. And Ragami fading can very well approximate Rishon fading and other complex fadings. So many times we approximate the actual fading using Nagami fading to get some tractable result, because these expressions are tractable while the Rishon fading expressions are a little bit difficult. So we start with a very simple case. In this first example, we are going to consider only the Rayleigh fading. So I'll talk about what is our system model here. The rest of the things are similar. You have a receiver at y0, and then there is a paired transmitter at x0. Then there are other transmitters xi at I distance. And if we fix our focus on the receiver y0, then all of these transmitters, including the desired one, so x0, xi, x1, they, if you consider the link to a particular xi, there will be fading in that link, right? And we can model the fading using the random variable hi. Right. So from the perspective of this receiver, we can see that each of the link has a fading hi. We can consider it as a mark, right? Uh, right, because each individual transmitter has a different random variable which is can be independent. So this hi would be a mark, and of course we assume a independent fading here. So these will be independent marks. So the transmitter location are modeled using PPP, and each transmitter xi has a mark denoted the random fading to the considered user. And it is important to know that if I change this receiver, right, all the fading may change, because now you are considering a different receiver, so every transmitter will may have a very different fading because the location has changed. So I have to reassign these marks, right? The distribution may be similar, but the actual values may change. Okay, so these marks are specific to this receiver, right? So if you want to consider a very general system where you have marks for every possible receiver, then you can consider a sequence of random variable hij, where hij denote the fading of xi to the receiver of the jth pair. Okay, so in that case, marks would be a infinite random vector, an infinite length random vector. But we are just focusing on one receiver, so let's assume this is just a random variable. Uh, and in that case, the instantaneous, right? So when I include fading into receive power, I call it instantaneous because this will keep on changing. So the instantaneous receive power would be transmit power into fading into path loss. Okay, and if I average it out, then it will be transmit power into path loss into expectation of fading. And if I take fading to be mean one, then this will be just transmit power into path loss. So I get the original receive power, which I were discussing in the previous case, the minute without fading. Right. So in this case, just to distinguish between them, this is called the instantaneous power, and the transmit power into path loss is known as the average receive power. Okay, so just note the difference between instantaneous receive power and the average receive power. Now the pair transmitter to be considered is located at r distance at x0 from y0. So the instantaneous receive power at the origin from the desired transmitter is given as transmit power c h0 r minus alpha. So this h0 is extra, which is the fading from the from x0. Similarly, the interference power from the I transmitter is known as PTCHI norm xi minus alpha. And the interference here would be given by summation over all those received powers, which are PTC, HI, XI minus alpha, right? And we particularly consider Rayleigh fading here. So in that case, this HI are exponentially distributed with mean 1, and they are independent of to each other. Okay, so assuming the independence of fading variable across transmitter is a very standard assumption, because fading changes very fast with space. So you can expect two links which are significantly different, which are actually different even by a small distance. You can expect them to be independent. So exponential means the probability that hi is more than some value h is e to power minus h into indicator that h is greater than equal to j. And if h is less than 0, then it is, of course, the uh, hi would, of course, be greater than 0, so it will be probability would be 1. So this is a CCDF of the exponential random variable. And once we have this interference and the receive power, the signal to interference plus noise ratio would be given as the receive power divided by interference plus sigma square. Right. And just to note that we are considering only a single receiver. In general, each transmitter is associated with a receiver. Therefore, there should be fading variable defined for each possible link between the ith transmitter and the jth receiver. To model this, each transmitter is associated with an infinite length vector hi, whose jth element denotes the fading to the jth receiver. Okay. Since we are only considering the 0th y0 as the receiver here, we will just take the 0th element of the vector hi and call it hi. Okay. And again, notice that there's an interference here is a function of x0 and depends on the phi after removing x0. The interference is coming from all the point process excluding the x0. We will talk about the assigner coverage probability of managed with fading. So assigner coverage of the considered user is given as probability that assigner is more than threshold. And the assigner is defined as transmit power C h0 r minus alpha divided by interference plus noise square greater than tau. So the derivation would be similar to the previous case. Only thing there would be h0 and hi in the interference term extra, and that may change. That is going to change the derivation as the expression significantly. So now because there's a one extra random variable here, I will rewrite in terms of probability that h0 is more than tau into I plus sigma n square divided by C pt and r minus alpha. Okay, so here we get this. Now there are one random variable is r and the random variable is h0. So to calculate that, I will first condition on I inside, compute the expectation with respect to h0 because that is simpler, and then I will compute the expectation with respect to I. So look at this probability that h0 is more than something. So when I condition an I, this become constant. So probability that h0 is more than some value, I already know the distribution. So this will be equal to e to power minus. So h0 is greater than h is e to power minus h. So this will give me exponential minus this term. Okay. Now I can, this is I plus sigma square, so I break into two parts. One is PTC inverse tau sigma n square r alpha, and another is PTC inverse tau I r alpha. Okay, so this is a constant term. It does not depend on I, so I can take it outside the expectation here. And this one is inside the expectation. Now this look like this. If you look at this, this is whole a constant variable. PTC inverse tau r alpha is a constant. So this is expectation with respect to expectation of exponential minus some constant s into I. So this is nothing but the Laplace transform of I. So evaluated at that constant. So this will be same, and this will be Laplace of I evaluated at PTC inverse tau r alpha. So the remaining is to compute the Laplace transform. If I know that, I will just put it here, right? So you have seen that in the past, when I was looking at this expression, it depends on the CDF of I. And even if I know the Laplace transform, it was difficult to convert CDF to, the Laplace transform to CDF. But here, because of this random variable, the expression itself comes out in terms of the Laplace transform, right? So this is very simpler than the previous non-fading case. Now let us compute the interference. Let us see how we can compute that. Right, again, what we do is we construct a new independent marked Poisson point process xi which is same density, and define I2 as the received power from all those base station, all those transmitters, which are given in the following way. And the I2's Laplace transform would be given as this one. And similar to the previous section, you can show that from the Selivniak theorem, the distribution of I, which is condition on a point, the distribution from the rest of the point is same as the interference from a independent PPP. Okay, so I distribution is same as I2. So Now, so I can replace the Laplace transform I by Laplace transform I2. So let us see how do I compute Laplace transform I2. So Laplace transform I2 is defined as expectation of e to power minus si2, and I2 is written as this. And again, this is in the form of Laplace functional of a function s pt hi lxi, right? I use the Laplace function of the mark ppt. So I get exponential minus lambda integration of 1 minus dx, and then there is the expectation with respect to the mark here, eh here. Okay. So the main difference is the from the non-fading cases, the presence of this fading variable, and because of that, the expectation with respect to h. Okay. Now I put back the path loss here, so that will be c into norm of x into minus alpha here. And then I can, this depends only on the norm. So I can just change it to polar coordinates. So when I convert to polar coordinates, the norm of x minus alpha become r minus alpha. They will have r dr, and then there is a 2 pi because this is not a function of theta. So integration with respect to d theta will become 2 pi. Okay. So I will get this term. So what I do here is this one I can also written an exponential expectation of h of 1. Okay, so I just take the expectation of h outside and I get this expression, right? And you will see this is simpler than first computing the expectation with respect to this and then computing the integration. Okay, so what you can do here also, you can compute the expectation with respect to h, right? Put the value here and then integrate it. That is also one way. Right, I apply this particular trick to take everything outside h. Then I do a transformation. Right. So see, when I compute expectation equal to h, this is in the inside integration, h is just a constant. So I can do this substitution as h cpt upon r alpha equal to 1 upon t alpha. So in that case, r is given by this, dr is given by this. When I do substitution, what I get here is this r dr will become s h cpt 2 by alpha into t dt. Okay, and this the whole thing will become just t to power minus alpha. So you have t to power minus alpha here, t dt here, and this scpt 2 by alpha, s2 by alpha will be outside, and this is constant, so this will be just outside the expectation, and only thing here would be h2 by alpha. Now notice that this integration is not a function of h, so I can take it outside the expectation. So the only expectation is here is with on h to power 2 by alpha. Okay, so now you can see this is constant, which is outside. This is again a constant, only a function of alpha. So expectation with respect to h is only here. Okay, rest term does not depend on what kind of distribution h has. Right. And so this expression, this I have already computed, that is equal to half gamma 1 minus 2 by alpha. So if I put it here, Laplace transform is given as minus pi lambda scpt 2 by alpha gamma 1 minus 2 by alpha into expectation of s2 by alpha. Okay, so basically the fading only affects the Laplace transform in terms of this moment, right? If the two different fading has the same moment, then you expect the Laplace transform to be same. Okay, so only difference here in respect to no fading here would be this term. Okay, but what fading has done is fading has changed this expression, right? Here instead of CDF you have a Laplace transform, so I can just push back the Laplace transform here and I'll get the actual value of the probability coverage. I don't have to compute its CDF. So once I put this back, what I get is right. Sorry, before that, what I do is I'll compute this moment of h2 by alpha for the exponential fading I've considered. So since h is exponential random variable, e h2 by alpha is given as this particular value, which is nothing but the gamma 1 plus 2 by alpha. So if I put this back, the Laplace transform is actually equal to this expression. Okay, so these are just function of alpha. And so when I put it back into the probability of coverage expression, I have to compute the Laplace transform at this value. Okay, so instead of s, I have to put this expression, and you will see the transmit power actually cancels here, and I only get lambda pi r square 2 to 2 pi alpha gamma 1 upon 1 plus 2 by alpha and gamma 1 minus 2 by alpha. Okay, and then you can use this result that gamma 1 plus 2 by alpha into gamma 1 minus 2 by alpha is equal to 2 pi by alpha cosec 2 pi by alpha. So once you put that, the expression you get is uh, exponential minus lambda pi r square tau 2 by alpha pi 2 by alpha cosec 2 pi alpha. This is from the interference multiplied by exponential minus ptc inverse tau sigma n square r alpha, which is from the noise. Okay. So you have seen that this expression is much more simpler and is in closed form. So and that is because of the presence of the fading. Right? So when the fading is present, the computation of assigned coverage is actually tractable, and you get a very simple expression. I will also compute a special case when the noise is zero, right? And that is possible when you have a high density so that the interference is significantly more than noise. So when you add noise to the interference, that is not going to change the expression or the performance will not. So in those cases, we can ignore the noise. So in that case, this first term would become zero. Okay. Uh, so sorry, this term becomes 0, so exponential of 0 will become 1. So only thing remaining would be this. So probability of coverage is given by exponential lambda pi r square t2 pi alpha pi 2 pi alpha cosec 2 pi alpha. Now you can notice that this is independent. Yeah, sorry. Yeah, it is independent of transmit power. Why? Because if you increase the transmit power of every base station, every transmitter, then the interference would increase in the same way as a single power, right? So they will actually cancel each other, right? But when the noise is present, that transmit power can help a little bit because it can help in counter the noise, right? But when the noise is zero, the transmit power you can put it anywhere and it will give you the same performance. We have derived the SIR coverage probability, which is given by the following format. We can let us see how we can derive some insights from the expressions. First thing we notice that SIR coverage probability decreases with R square, right? Sometimes people expect it to decrease with R alpha because the path loss is uh, CR L R minus alpha. So they expect if you increase R, the signal power will decrease by minus alpha. But actually the SIR coverage probability decreases exponentially with R square. Then if you notice that this is just a coefficient, lambda pi r squared gamma 1 plus 2 by alpha 1 minus 2 by alpha. So if I replace it by C dash, what I get is probability SIR more than tau is exponential minus C dash tau 2 by alpha. So SIR coverage decreases exponentially with tau 2 by alpha. If I make the threshold double, then you would expect potentially this to decrease by this factor. Now, one thing we also notice that the dependence on the distribution of I only depends on this moment. Right? So if you look at the Laplace transform expression, you only have this term. So if two fading have the same moment, where same 2 by alpha moment of the edge, then they will have the same interference, right? Even if their distribution is different. Okay, so exact nature of fading does not matter in the computation Laplace transform. This fading actually matters. This movement actually matters. So if I define lambda dash equal to lambda into ES2 by alpha, then I get the SIR coverage probability as lambda dash pi S2 by alpha gamma 1 minus 2 by alpha, which is same as the Laplace transform of the interference in the no fading case with density lambda dash. So this means the Laplace transform of interference in a minute with some fading edge, where transmitted density is lambda, is equal to the Laplace transform of interference in a minute with no fading and the density lambda ES2 by alpha, thus implying the equivalency in the distribution of these two interferences. This also gives a relation between the interference in the case of no fading and there is some fading there. So how another way this expression can help is let a designer know how to choose different parameters, right? Let us see an example. Suppose a system designer wants to build a system such that he can guarantee 90% of the time, 95% of the time, user will get assigner above 10 dB, right? And the system parameters are like that: alpha equal to 4, lambda is this, noise is minus 60 dB, C and 1 is just assumed to be 1. So what is the transmitter receiver density? He should specify that you should not put your receiver at a distance away than that. So I know the assigner coverage probability is given by this, right? I put back the expression and say that I want it to be equal to 0.95, right? And then you solve this expression, you get a quadratic equation here. And once you solve it, you get R equal to 8 meters. It means if you put R equal to 8 meters, you would get this the desired performance you are expecting. See some other para performance metrics also. One is transmitter success probability. So let us assume that T0 is the assigner threshold for a transmission to be successful. Right. So this means that normally you expect that if the assigner threshold is above some assigner is above some threshold, you can successfully decode it. This means the communication is successful, and the assigner is below this, it may not be possible to decode it. So the transmission success will occur for a pair if the assigner at the receiver of that pair is above this threshold, right? So in that case, the transmission success probability is same as the coverage probability evaluated at that T naught. Okay, because this is the probability that the coverage, the assigner is above T naught. So this will give me the success probability. Now, successful transmitter density means, so in the past we have seen that if you look at these expressions of SINR coverage, you will see that as lambda increases, this decreases exponentially. Right? So that is because with a higher lambda, you expect more interference, the coverage will decrease. Right? So that is, so someone can just say that it means you should take the lambda very low. Right? But that is also not correct, because when you have small lambda, you have very less devices, right? So what is the use of the network if you don't have enough devices, right? So to model these two effects in one framework, we come up with this successful transmission density. So it means that it calculates average number of transmissions in a successful transmission in an area. So notice that average number of transmission in a unit area is lambda, because they are lambda devices per meter square. So this will be your average number of transmission that is going on if everyone is transmitting. And the success probability is PS lambda. So the number of successful transmission in a unit area is lambda into PS lambda. So this kind of tells that how many transmissions, successful transmission are going on, how many bits are exchanged in a per unit area, kind of. So if this tells you if lambda is small, all the PS lambda will be high, lambda will be small. So overall number of successful transmission will be small, which is not desired. So there should be some optimal lambda, which you can say that uh, uh, this will increase my successful transmission density. And also it makes sure you have to make sure that the quality of service doesn't go beyond a limit, that you don't put so many lambda network devices that everyone is failing. The success probability becomes very small, even though lambda into p becomes high, right? So there's a term called transmission capacity. So for that, we first fix P0 as the minimum success probability to ensure quality of service. Your success probability should not be below that. Otherwise, there will be a lot of failed communication, and then you have to retransmit so many times. So transmission capacity is now defined as the successful transmit density at the maximum supported transmission density. Okay, so this means that you so transmission successful transmission density is what? P0, the success probability multiplied by density. But you want to choose the density which is which is maximum, such that the quality of service is maintained. It means you want to choose a lambda for which success probability is more than P0. Okay, you want to choose that density, and for that you want to compute the you if you take that density, the successful transmission density would be P0 into lambda. So how do I compute this? Um, Let us first take the interference limited case. So in that case, let us solve the constraint first. So you want coverage probability to be more than P0. Coverage probability is given by exponential minus lambda A tau naught 2 by alpha, and this A is the coefficient we discussed earlier. So from that we get lambda A tau 0 2 by alpha should be less than log minus log P naught, and from that you get lambda should be less than this value. So if lambda is below this value, you will have a coverage more than P0. And since you want to choose the maximum lambda, which has take the upper boundary, which means I will take this value log P0 as A T naught 2 by alpha. So my successful density, transmission success density would be P0 into this value. Okay. So this is my successful transmission density, which can make sure that the P0 is supported. Similarly, if there is a noise, you can include that effect also. You can solve it, and similarly, you get this constraint, and you just choose the maximum upper bound of sorry, the maximum value lambda possible, and multiplied by P0 to get the transmission capacity. The third parameter which we want to discuss also rate coverage, right? So assigner coverage is fine. You want to make sure the assigner is above some threshold to ensure that your transmission is successful. But also the other factor would be important. Important would be what is the data rate you are able to transmit, right? And to compute that, we have this rate coverage parameter, which tell you that what is the probability that the rate of the typical pair is more than some threshold. Okay, so for that we first notice that if W is the bandwidth of each transmitter, then you can compute the maximum achievable rate, which is given by W log 1 plus SINR. Okay, which denote the maximum number of bits transmitted per second. And the assigner is a random variable, so rate is also a random variable. So what I would calculate here is the sum characterization of rate, right? So one thing would be the rate coverage probability, other can be median or mean rate, other statistical averages. So first talk about the rate coverage probability, which is defined as the probability that the achievable rate of a typical pair is above threshold rho. So the probability that rate is above threshold rho is equal to, if I put the expression of rate here, W log 1 plus assigner, that I want to be more than rho. If you solve it, you get that assigner should be more than 2 to power rho by W minus 1. Okay. So this is the probability assigner is above some value. So that is given by the coverage probability calculated at that value. So this is nothing but the coverage probability, assigner coverage probability at 2 rho by W minus 1. So once I have the assigner coverage probability, I can also compute the rate coverage probability. I'll put this value back to the expression and I get this rate coverage. Okay. And then I can also compute other parameters such as mean rate. Mean rate would be the expected value of rate. And then you can compute that by integrating the CCDF over D rho, right? That is that way you can compute the mean. If you want a median rate is what? It's a median rate of a random variable is defined as the threshold, which will give the probability that rate is above that threshold at least half, right? Or below that value is also half. So to calculate that, you have to just invert the rate coverage probability. You have to make sure that the rate coverage is equal to half. So you just compute that row, which will give me that. Right. So this, you can say the median rate is equal to RC inverse function calculated at 1 upon 2. Right. Similarly, percentile rates are defined as thresholds, as that suppose 75 percentile rate would be thresholds, as that 70% of the time rate is above the threshold. Right. And that you can also calculate. You just put the rate coverage to be 0.95, invert it to compute the threshold row, which will give you this percentile rate. So now let us discuss a variant of MANET, which is known as MANET Aloha. So Aloha protocol, which is named on a city in Hawaii. It's a very simple protocol, which just means that each transmitter decides randomly and independently of other transmitters when it wants to transmit. Okay. So normally what happens if the density of a network is significantly high, then if every transmitter transmit, you will not get any, there will be so much interference that none of the transmitter will get any, another receiver will get any data. So in that case, you want to set some probability of transmission, and without the need of any coordination, every transmitter just randomly wakes up with probability p, right, and just transmits, right. And because of nowadays, at any point of time, on the average, there are less number of transmitters, the interference goes down. Okay, so this is a very simple protocol which actually works. Uh, so we may have multiple transmit receiver pairs, but not all of them are transmitting at any timestamp. At any timestamp, randomly some transport nets are activated. They are independently of other transmitters also, and they transmit to their receiver without any coordination among other transmitters. Okay. So the probability that any transmitter will transmit is a P, and there are other more complicated transmission strategies which you can think of. But let us just see how we can compute the performance of LOR. So just to be sure, in MANET, all transmitter receivers are working, transmitting. And in this case, a certain time instant, red denotes the active transmitter link. So randomly, every link decide to be either transmitting or idle. And all the transmitters which are active, they transmit, right? And of course, the receiving will depend what is the current assigner at that density. And then the next end, other transmitters independently can become active, and so it may happen the same transmitter is again transmitting because it's a random event, or there are new they become idle and the new transmitters are also coming. So if I fix an instant and take some arbitrary pair which is transmitting, from the perspective of the receiver of the selected pair at a particular instant, the interference is caused by only those transmitters which are transmitting at the current instant. Okay, let's call them active transmitters, and the rest of the transmitters are idle. So what is the point process denoting the new active transmitters? So know that because this is a independent selection, so every transmitter of the original point process randomly decides with probability p whether it wants to be active or not. So it's like an independent thinning. So the point process of the active transmitter is a thinned version of the original point process. So it is also a Poisson point process with the density lambda into p. Okay, this is from the independent thinning theorem. Because I am independent thinning the PPP, I'll get another PPP with the density lambda, right? So, and then all the transmitter which are not active, I can just ignore them because they are not causing any interference, right? So if you want to compute the Laplace, the interference of the Laplace transform of the interference of from these active base station, every active transmitters, then you have to take the density lambda p, right? If I put that back, right, in the Laplace transform expression, so only changes here in the density of the lambda, rest parameters are same. Only that the active density is not lambda, but the lambda p. So I get the Laplace transform, right? And if you decrease p, you get a less interference. If you increase p, you get the more interference, right? And if I know the LIS, then I can compute the SINR coverage, which is given by exponential of this term because of noise into exponential of Laplace transform evaluated at the that coefficient. So I get this expression. Okay, so the expression is same, only the density term is different. Instead of just lambda, now I have lambda p. Okay, and you can notice that if I decrease in p, right, if I decrease this term, then the SINR coverage probability will increase, right, because the interference will go down, right. Or you can directly say if I decrease p, this term would decrease, so the exponential minus term will increase and the SINR coverage will increase. So right. So let us ignore other terms. R squared, this thing, just make it A. So what I get is the Sierra coverage property is mother exponential A lambda P tau 2 by alpha, right? And at this, I have just included all the other parameters in terms of A only. And I want to focus on the interplay of lambda P and tau. Okay. Now you can see if the P is decreased, the Sierra coverage probability increases, right? So why don't we just take p equal to 0, right? Here I'm ignoring noise for now, right? Even if the noise is there, you can, with the significant density, you can assume the noise is not coming into picture. Okay. You can of course analyze this also in presence of noise. The more of the concept will be similar. So if you see this p, if you decrease, SI coverage probability will increase. Right, then someone say, why don't you just take p equal to 0? In that case, p equal to 0, then this SI coverage will be 1, right? Right, and that is not possible because if you think, if you take p equal to 0 means the transmission probability is 0. It means no network is able to transmit, right? So if no network is able to transmit, what is the use of having low interference, right? Of course, the interference will be low, but if no one is transmitting, you're not utilizing the network, right? So that is also not desirable. So you want something that you want to have some density also, so that there is active communication going on, and you want also the interference is not that much, right? So here one thing is to optimize the number of successful transmitters per unit area, right? And that actually kind of tells you how many bits you are transmitting, right? If there are multiple transmitter, and if you want to utilize the network, you want to just make sure that most of the transmitter pairs are transmitting to their receivers. So the number of bits which are exchange bits which are going on in network is high, right? So that I define as a spatial throughput. Spatial throughput is defined as the average number of successful transmissions occurring per unit area. So product of number of active transmissions per unit area multiplied by the probability of transmission success will give you spatial throughput, right? So let's assume the successful transmission requires a SINR threshold of T naught. So in that case, the spatial throughput is given as the density, which is lambda p, multiplied by probability that SINR is more than T naught, which is given by this, right? And what you want to make sure uh, that you this special throughput is maximum, right? So you can see now with p, this will of course increase. If you decrease p, this will increase, but this will decrease. So there's a trade-off here, right? So optimal value of transmission success probability would be to maximize the special throughput, right? So the optimal value of p, which can optimize special throughput, is given as the argument of the maximization of tst, okay, which is given by lambda p into this, right? And if p is greater than p opt, if you are transmitting with a probability more than this optimal, your interference will be high. If you are below this, then your interference is small and you are not utilizing the space properly. Okay, so how do I compute this? Let's take the SIR case. uh, to something to be maximum, local maxima, you have to make sure the differentiation with p is 0. I'll put the expression back, I solve it, and what I get is p optimal is equal to 1 upon lambda t naught 2 by alpha c. Okay, so and what if this value is more than 1? Then you just choose 1, right? So this means we can, so if you are getting a value less than more than 1, it means your density is very low. And it means you are, even if you transmit, everyone is transmitting, you are not achieving the optimal density. So in that case, you can actually go increase lambda. That will just increase the overall density. And then you can choose P if the coverage probability is, if the set throughput is not what you desired. Uh, Sometimes we can also have another constraint that you want to have the optimal transmission probability, but you want to still make sure that the success probability does not go below a particular value. So in that case, so you can see this example. Suppose you come out to a subsystem there where you optimize this spatial throughput. Right, but you have chosen one piece such that the SIR coverage probability is like 0.05. Right? So even if you're getting very maximum number of transmissions, only 5% of the transmission is successful. It means every transmitter has to redo 95% of the communication. And that is not desirable because every redo requires another set of overhead, right? HRQ and other things. So you want to also make sure, and that's also called latencies. So you want to make sure that even if to get a throughput, maximum throughput, while satisfying a particular quality of service, right? So in that case, I would say that I want to maximize TSP, the special report, while maintaining that the coverage probability is above P naught. Okay.